Assalamu alaikum. Hope you are doing fine. We have obtained the expression for electric field due to a charged wire and a charged sheet with the help of Gauss Law. In this video, we are going to get the expression for electric field due to a charged spherical shell using Gauss Law. For that, I consider a charged spherical shell having a radius represented letter capital R. Here O is the center of this charged spherical shell. Now I take a point P outside this charged shell. At point P I am going to find the electric field due to this charged spherical shell. Here P is taken as point. Yes, where I am going to find the electric field due to this charged sphere. Now I draw a sphere which encloses this charged shell. This sphere that I have drawn now passes through point P. Here point P is a distance small r from O. Here the distance is small r. Here small r is greater than capital R. It is obvious from the diagram. So at this point P I am going to find out the electric field due to this charged spherical shell. If you take any point of this sphere, you will find the magnitude of electric field due to this charged shell remains the same. So we can say that electric field is constant or uniform around this charged shell. So is constant. We know to get the electric field we use Gauss Law. Whenever we apply Gauss Law, we take a closed surface. We call such a closed surface as Gaussian surface. This sphere or this closed surface is nothing but Gaussian surface. So I am going to apply Gauss Law to get the electric field at point P due to this charged spherical shell. What is the Gauss Law? It says that 5E which is equal to closed interval of E vector dot dA vector is the expression for electric flux, where it is equal to charge upon epsilon naught. Here epsilon naught is permittivity of free space. Okay. Now here the closed interval is taken on Gaussian surface. Gaussian surface. So I write it here. So this is nothing but Gauss Law. What is this? Gauss Law. I write it here. Gauss Law. With the help of Gauss Law, I am going to get the expression for E. We know one thing. The dot product of vectors. If you have A vector dot B vector, then this can be expanded as A dot B cos theta. By following the same method, Here E vector that dA vector, E vector that dA vector can be written as EdA cos theta. But here, one thing I forgot to mention. Suppose the charge Q is greater than 0. When I say a charge is greater than 0, that means the charge is positive. In such case, electric field produced by those charges acts outward. So, electric field act outward, project outward. Suppose this shell have positive charge, then the electric field will be acting outwards. This is what it means. On another hand, if Q is lesser than 0, that means the charge is negative. When the shell carry negative charge, electric field will be acting towards it. So, electric field acting inward. You remember this. So, by having this in mind, here I assume that the charge carried by this spherical shell is positive. So, electric field acts outward. So, the direction of electric field is given by E vector and dA is the area element taken on this Gaussian surface. Here, dA vector is the direction of that area element. Now, in this case, when the charges are present on this spherical shell is positive, then E vector and dA vector both will act in the same direction. When these two act in the same direction, then theta is taken as 0 degree. Okay. So that I mentioned here. I take a theta equals to 0 degree. Then cos of theta equals to cos of 0 degree. That is equal to 1. It is known to us. Now I am going to substitute these things in this equation in Gauss law. So what I will get? I will get this. 5e is equal to closed interval of E vector dot dA vector, and in the place of that I write E dA cos of 0 degree. Yeah, Gaussian surface. We know cos of 0 is 1. Now this is equal to, one thing I forgot to mention here is nothing but Q upon epsilon naught. Yes, Q upon epsilon naught. This can be represented as closed interval of EdA equals to Q upon epsilon naught. Stands for Gaussian surface. Gaussian surface. Now here we have omitted 5e. Then 5e actually stands for this term. So we have to write both at the same time. So I have not mentioned this one here. Then we will continue with this term. Now I told you earlier, here E is a constant, because if you take any point on this Gaussian surface, there the electric field will have the same value. due to this uniformly charged shell. Okay, so in that case, as E is a constant, we take it out of the integration. So this is written in this manner: E closed integral of dA equals to Q upon epsilon naught. Okay, for Gaussian surface. Okay, then I write it this way. Here, integral of dA is written as A. Q upon epsilon naught. Now, let me tell you why I have written A in the place of integral of dA. We know integral of dx is x. In a similar way, integral of dA is nothing but E. So the same thing we have for a closed integral as well. Closed integral of dx is x. So closed integral of dA is E. Okay. So the opposite of differentiation is integration. When we integrate a differential term, the differentiation gets cancelled and we get this thing. This is how we have obtained this. Now here A is the total area surface of this sphere which surrounds the charged shell. So we know the area of a sphere. We know area of a sphere is 4 pi r square, that I am going to use here. That this one mentioned as E. In place of A, I write 4 pi r square equals to Q upon epsilon naught. Then what is my aim? My aim is to get the expression for E. So it is obtained using cross multiplication. E is kept here as such. The remaining terms are taken on that side. So I write it like this: 1 by 4 pi, then epsilon naught, which is present here as such, then Q upon what? R square. R square. This is the expression for electric field at a point outside the charged shell. No? Okay. What will be the value of E when the point P is present on the shell? I'll say, take a case 2. Case B. What is that? At a point, electric field at a point on the shell. On the shell. So, when the point is taken on the shell, in such case, the small r will be equal to capital R. Small r will be equal to capital R. And what will happen? See, this expression will be written as something like this: E equals to 1 by 4 pi epsilon naught Q upon, in the place of small r, I write capital R. Capital R square. This is the electric field at point P taken on the surface of the charged shell. Okay, I box this. Now I am going to find out the value of electric field when the point P is taken inside the charged shell. So for that, I draw the diagram. So take the same shell having a center bow and the radius is capital R. Now I take a point here, this point P taken inside the charged shell. Then with respect to this, I draw a Gaussian surface. This is the Gaussian surface. Here the radius of this Gaussian surface is taken as small r. So in this case, if you look at carefully, you may find r is smaller than capital R. It is the reverse of first case. The first case we have taken r small r greater than capital R. Here in the third case, in case C, we take a small r smaller than capital R. Right? Okay. Now I write this. Case C. Electric field at a point on the shell. Inside the shell. Inside the shell. So here, small r is lesser than capital R. Underline this. Now, let's see what are the changes that I am going to make here. In this case, I will follow the same method. I will take a Gauss Law. This Gauss Law is this. Closed integral of E vector dot dA vector equals to Q upon epsilon naught. Now, this is here is on closed integral is taken on Gaussian surface. The Gaussian surface is the closed surface. Then we follow the same method here. Then again, the cos of 0 is taken as 1. The angle between E and dA is a 0. We get this closed integral of dA cos of 0 degree for Gaussian surface. It is equal to Q upon epsilon naught. Then this thing will be obtained by following the same method or something like this. Here is a 0 like this. Closed integral of E dA equals to Q upon epsilon naught. So Gaussian surface. Gaussian surface. Now, here you need to keep one thing in your mind. The thing is that there is no charge present inside this charged shell. Charge are present on the shell, but there are no charges present outside the shell. So, when there is no charge present inside the shell, in such case, the value of Q is when there are no charges. When there are no charges, Q is taken as 0. When the Q is taken as 0, 0 upon epsilon naught is 0. So, E is taken as 0 here. This shows that when you take a point inside the charged shell, the electric field is 0. You remember this. We call this phenomenon as electrostatic shielding. I repeat, a point inside a charged shell have a 0 electric field. So, E is equal to 0. Let me elaborate this final expression that we have obtained for the case in which we have taken the point P inside the charged shell. How do we get a 0? Here, the term is a closed integral of E d A equal to Q upon epsilon naught. This closed integral for Gaussian surface. Now here, when E is a constant, as we have done earlier in this case, here we taken E constant. Similarly, we will keep the same here. Then, if when E is constant, it is taken outside the integral. Then we get closed integral of dA equals to Q upon epsilon naught. Here, Gaussian surface. Here, closed integral of dA. No? There is nothing but A. By following this expression equals to Q upon epsilon naught. You know, for a sphere, A equals to 4 pi r square. Area of the sphere is 4 pi r square. That I use here. So what I get? E equals to 4 pi r square equals to Q upon epsilon naught. Now, as I have mentioned here, the charge inside the shell is 0. So, this term, since Q is equals to 0 inside the shell, so I write it this manner: E into 4 pi r square equals to the plus of Q, right? 0. 0 upon epsilon naught. We know when 0 is divided by something, the value obtained is nothing but 0. It is equal to 0. So, this gives us E 4 pi r square equals to 0. When I take a 4 pi r square that side, again the value obtained is nothing but 0. Is equal to 0 upon 4 pi r square. It is nothing but 0. So, electric field is 0 in case of a point taken inside a charged shell. This holds good for any kind of charged object. Okay. Then I am going to draw a graph between electric field and R, that is distance. Okay. R here. At this point, the radial distance is a 0. When the radial distance is 0, that means I will show you. Yeah. It does. At this point, R is equal to 0. As you go away, we take at this point. This is capital R, this distance, radial distance. Suppose I have a point somewhere here. Then this radial distance taken as small r. This taken as small r. Point P. Okay. In that way, at the center, just now I have told you, electric field is 0. But here, I take one point here somewhere. It is a capital R. That means at point taken on the surface of the charged shell. So there the electric field is represented by this expression. Here it is E is equal to 1 upon 4 pi epsilon naught capital Q upon R square. This is the value of electric field at this point. Then as we move away at R, the value of VE will reduce. Okay, so there it is taken as here at point R. Suppose this is R. R is present somewhere here. So in that case, E is taken as 1 upon 4 pi epsilon naught Q upon small r square. Small r square. Okay. So this is I find it very difficult to understand. So I show this to you with the help of a curve. Now, say at this point, the value is more. So we have R here. As we the maximum. As we go away, the curve is keep decreasing, coming close to x-axis. So here at point R, E value is large. At a point small r, the E value is reducing. This clearly shows that as you go away from the surface, electric field decreases and is maximum on the surface of the charged shell. Whereas at the center, the electric field is completely 0, that I mentioned here. Electric field is 0. No, at the center. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.